and today she's presenting this work about decoherence, non-Markovianity, and quantum estimation in qubit systems, subject to color noise. That is one of the topics of her PhD thesis. Okay. She will be here for 4 months.
Yeah.
And she's actually already here for months, so she will be here for the next 3 months. And also Antonio Mandarino, is somewhere there, will be with us visiting also from the Università di Milano. Okay.
Okay, thank you. Good afternoon. And first of all, let me say thank you to give me the possibility to do this talk, to present my work here today. My work, which is, as Roberta has read, about decoherence, non-Markovianity, and quantum estimation in quantum systems that are interacting with a classical fluctuating field. So the reasons behind this talk is that, as you well know, every quantum system interacts with its own environment. And this interaction usually is detrimental and destroys in particular the coherence and the quantumness of the system. And this is bad because the quantumness, like the quantum coherence, are the key ingredients to perform like quantum information processing or reliable communication protocols, or quantum communication protocols, or quantum communications. So it would be nice to have an insight on the mechanism, for example, of the coherence of these quantum systems that are interacting with the classical field. And why are we interested in classical field? Is because in the recent years there have been a lot of interest in solid-state qubits. For example, like superconducting qubits. And if you read the literature, you see that these superconducting qubits are considered good candidates for the quantum to implement the quantum computation, but they have a withdraw that which is that they are very sensitive to the fluctuations of the environment. And in particular, a lot of studies have shown that these fluctuations are characterized by 1/f spectral density, power spectrum, where f is the frequency. And so what we want to do is to study a simple quantum system, like a qubit or 2 qubits, and let them interact with a classical field which has a spectrum that is proportional to 1/f, and then to study the dynamics of the quantum correlations to see how they which is the effect of this external environment on the quantum correlations. And also, I will tell you something about a complementary view, that is, since these qubits are very sensitive to fluctuations, the idea is to use them as a quantum probe to characterize, for example, the spectral properties of the environment. So, what I'm going to talk about in the outline of the talk, I will give you just some definitions, like, for example, the entanglement, and I will present the noise model and the system environment model, and then I will show you our results about the dynamics of quantum correlations, the behavior of the non-Markovianity measure in this system, and then I will, as I told you, introduce the tools of quantum estimation theory that allows us to use a qubit as a quantum probe for a complex environment. So let's start by considering bipartite states, quantum states, which is bipartite system states, which is a system divided between 2 parties, and usually in quantum information they're called Alice and Bob. And I want to study the dynamics of quantum correlations. So first, let's say something about correlations. You know that if you have a factorized state, and you have a global density matrix of the 2 subsystems A and B. If the state is factorized, then you know the global state is factorized, there are no correlations. But if you consider a separable state, that is a convex combination of product state, you see that this state has correlations. And the feature of separable state is that they can be prepared by local operation and classical communications. This means that Alice and Bob, they both can perform locally on their subsystems some operations, and then they communicate classically, for example, over the phone. And in this way, they can prepare the states, called separable state. And states which cannot be written in this way are called entangled state. So the definition of entangled state is that they are states that cannot be written as separable states. And the feature of this why are entangled states important? They're important because they display correlations that are not classical, that have a quantum nature. And to see how why I said this, let us consider, for example, a Bell state. Bell state, and I can write, they are, okay, pure state, and I can, they are written as a linear combination. Okay, so they are in a linear combination. For example, here I depicted the state psi plus, where consider the green part belongs to Alice and the red of qubits in state 0, 1 plus. For example, Alice perform a measurement on her subsystem. You have the wave function collapse on state finds 0 on a party. You know for sure that the wave function of Bob's part collapses into the state 1. So what you see is that you have some correlations that are not of don't have a classical nature, they're quantum, due to the fact that we have a superposition of state, of course, and okay, this kind of correlations cannot be described in the classical world. So this is for entanglement, and there are a lot of criteria in the literature to say if a state is separable or entangled, and there are many measurements of entanglement, and usually they don't coincide. But in this talk, I will only talk about 1 or 2 qubits. So in this case, all the measurements coincide, and here I will present one, which is called the negativity. And the negativity measure for entanglement comes from the Perez PPT criterion for separability, which states that a quantum state is separable if its partial transpose has no negative eigenvalues. And this is a necessary condition. So, years later, it was in 2002, was introduced the measurement of negativity, measured to quantify the amount of entanglement in a system, which is minus the sum of the negative eigenvalues of the partial transpose of a density matrix. Where with partial transpose, partial transpose means to do the operation of partial transposition only on one subsystem. For example, here we do the partial transpose only on Bob part. And then if you sum the negative eigenvalues you obtain, this is a measurement of the entanglement. And the good thing is that for 2 qubit systems, this is a necessary and sufficient condition for entanglement. So this is about
what is the condition to be n be non-zero?
N, N is between 0 and 1, and this is 0 non-entanglement, and 1, for example, Bell state, maximally entangled state. So, okay, I told you entanglement is a kind of quantum correlations. And for a long time, it was believed that entanglement was the only kind of quantum correlation, in a sense that a separable state was believed to have only classical correlations. But then in 2001, two papers came out from 2 dependent groups, and they discovered or stated that actually separable states have also some quantum features, some quantum correlations. And this is due to the fact that in quantum mechanics, when you do a measurement on, for example, on one part of my global system, for example on V, this measurement is changing the physical state of the system. And this is something that in classical mechanics we don't have, a measurement that doesn't alter the state of the system. And using this fact, they could introduce these new kinds of quantum correlation, they called quantum discord. And to give you an idea from where this quantum discord comes from, you have to consider first the classical mutual informations. You know, if you have 2 random variables, x and y, and you want to calculate the correlations between them, you can use the mutual information. The global correlations between them is given by the mutual information, which is written in terms by introducing the mutual information information in this expression J, and classically these two expressions. But now, if you want to do the quantum version of the mutual information, what you do is that for the first expression I, you don't have problems. The only things you have to do is substitute the Shannon entropy with the von Neumann entropy, and you obtain an expression which actually gives you the total amount of correlations in a system. But then when you want to put J in a quantum form, you have a problem, because as you can see here, you have the conditional entropy. These terms gives you the information you have on subsystem A once you've measured subsystem B. And you see we have a problem, because it involves a measurement, and the measurement changes the state of the the state of the system. So this quantity actually is ambiguous. And what the authors did in their paper was to define the classical correlation of a quantum state as the mutual information J obtained by adopting the least disturbing measurement. This means they rewrote this expression in this way. This sum is the conditional entropy. This term is the conditional entropy. And then what you have to do to describe the classical correlation, you have to maximize overall possible measurements on B, because you want to obtain the measurement that least disturbs the system. And so these are the classical correlation. I is the total correlation of the system, and the quantum discord is the difference between the total correlations and the classical correlations. So it gives quantum correlations. And so the very important thing in all of this is that you can have separable states that exist separable states that can have non-zero quantum discord. And the fact that you don't have entanglement doesn't imply the fact that the correlations are only classical. You have also quantum correlations. And these non-classical correlations, as described by quantum discord, are something that is more general and fundamental than entanglement. So this was about the quantum correlations. And now I can describe you the system I'm interested in and I want to study. So I will consider two qubits in a maximally entangled state, so a Bell state. And these two qubits are non-interacting, but they are interacting with a classical environment. And in particular, because the two qubits does not interact. And what I do, the single qubit Hamiltonian, HAHB, can be written, for example, here I show you two examples. Let's focus on the first. I have a first term which describes the energy, the levels energy splitting of the qubits. And then the second term is the stochastic term, because you have these C of T terms, which is a coupled. For example, in here with sigma Z, it gives you fluctuation in the energy splitting of the qubits. And for example, if I consider the second Hamiltonian in here, we have a stochastic process which X, which gives you it's related to the transition between the two levels of the qubits. So, and okay, nu is the coupling constant. A stochastic term, dependent stochastic term. And to say something more about this stochastic term, as I have a spectrum which is proportional to 1 over f to the power of alpha, where if alpha is equal to 1, we have the very famous 1 over f noise. But in our study, we considered a range for alpha which goes from 0.5 to 2. And yeah, and so this is it's a classical noise, and it arises from non-Gaussian process. Non-Gaussian process is a process that cannot be fully characterized using only its mean and its variance. You need higher order statistics to fully describe it. And if we want to say something more about this, how this term should be written, we know from the literature that 1 over f to the power of alpha noise arises from a collection of bistable fluctuators, in particular random bistable fluctuators, and I will tell you in a minute what I mean by this. And the reason why we are so interested in this noise, I've already said that, but is because in the literature in the last year, a lot of studies have been devoted to the understanding of this kind of noise, in particular in its origin, which still now is an open problem actually, because it affects superconducting qubits. And so we are very interested in analyzing the effect of this kind of noise on the quantum correlations. So we focus on two different scenarios. We can have independent environments where the two qubits interact with each with its own collection of fluctuators. So we can have a common environment when both qubits feel the effect of the same collection of bistable fluctuators. And that can switch between two values with a certain switching rate. I will call it gamma. And quantities that switches between two values are a source of random telegraphic noise, which is characterized by an exponential decay of the correlation function that is a Lorentzian spectrum. And when I say that we have to consider a collection of bistable fluctuators, I mean that this C term is described as a sum of this qj quantity, which are quantities that can take value plus or minus 1. And the switching rate between this plus and minus 1 is unknown. Fluctuator. So the switching rate is unknown and is taken from a statistical incentive. Distribution of the switching rates, that if you look at this expression, it's small, but it's proportional to 1 over gamma to the power of alpha. So once we have the probability distribution of the switching rates, you are able to construct to build the stochastic term C of t. You can then calculate the evolution. This evolution operator contains a stochastic. I define this phase as the and then once you have the evolution operator, you system interacting with the environment. But since we are matrix, what you have to do once you have this density matrix, you have to. And in our case, the degrees of freedom of the environments are the time sequencing, C of t, because this is a random, a stochastic term, so you can create as many different time sequences, potentially infinite times different time sequences. Degrees of freedom of the environment is the switching rate, because the switching rates are unknown. So you have this collection of gamma, but you don't know their values. So first of all, you perform the average, the ensemble average over the time sequences, and here, instead of C, I calculated the average over the phase phi because they are the same, and it gives the same result, but the point is that the distribution of the phase is known from the literature, so we are able to calculate this ensemble average. But then once you've done this average, you still have the dependence on the random switching rates, so you do another average over the switching rates, and this we can do because you know the probability distribution of the switching rates. And they have two expressions, one for independent environments and one for a common environment. And so we calculated this, and we obtained as our result the density matrix of the qubit, the two-qubit system, which is described as a mixture of Bell states. And you see the coefficients depend on some function. We can have a monotonic behavior or can have display oscillations. And this different behavior depends on the ratio between the gamma and the coupling constant. But once we have the form of the density matrix, we can now calculate the quantum correlations, both the negativity and the quantum discord. And we were able to calculate, analytically, semi-analytically, let's say, because this integral actually you have to do it numerically. And what we one famous 1 over f noise, and what you see is that the quantum correlations, both negativity and discords, decay monotonically in time. So they are just destroyed by the interaction of the environment, and they're destroyed faster if the number of oscillators that model my environment is larger. But then the situation is different if we consider a higher value of alpha, because what you see is that quantum correlations display revivals. There is apparently they're dying, but then at some point you have a revivals. There is a rebirth of quantum correlations. But if you increase a lot the number of fluctuators, what you see is that you still have the monopolic decay. Actually, if you take alpha, for example, like alpha equal to 2, what you see is that the quantum revivals are the peak, the height of this peak is very large, and also if you consider a high number of fluctuators, quantum revivals survive. So the higher the value of alpha, the better it is for quantum correlations, because you have revivals that can survive also for a large number of fluctuators. These pictures are show the case of independent environment, and here I show the case of common environment, and you see that the qualitative behavior is the same, but in the case of a common environment, if you compare, for example, f equal to 1, the quantum correlation are more robust in the sense that they survive a little more, survive more, for a longer time with respect to the case of independent environment. And also another effect is that you consider an alpha, which is different, greater than 1, it doubles, the high of the peaks is larger and it doubles the number. So common environment, let's say, it's better for the quantum correlation, for the survival of quantum correlations. And so this is for what concerns the quantum correlation, and I told you in the beginning, because we are interested, because they are considered a resource for the quantum information processing. But in the last year, another figure of merit was addressed as a resource for quantum information processes, and which is non-Markovianity. In here, I'm not talking about the Markovian or non-Markovian character of the environment, but about the Markovianity or non-Markovianity of the dynamical maps, of the dynamics of the two qubits. And so, in the let's say in the context of quantum information theory, there are a lot of measurements of Markovianity, and here today I will just present one, which is the Breuer-Lane-Pilo measurement, and they describe Markovianity as information backflow. Why is that? Because they say that if the dynamics of the quantum system is Markovian, then this dynamics tends to reduce the distinguishability between any two quantum states. You take two quantum initial states, they evolve under a Markovian dynamics, and the distinguishability between the two will go to 0. And this is interpreted as an irreversible loss of information. Information leaks out from the system. But if you have a non-Markovian dynamics, then this means that you have at least some time intervals when the distinguishability is restored. You have a growth in distinguishability, and this is interpreted in terms of backflow of information. You have some information that flow back, let's say, from the environment to the system. And so, since in quantum mechanics, the quantity that is related to the fact that you can successfully distinguish the quantum state is the trace distance. The trace distance is the object we are interested in. The trace distance between two quantum states is an object that is defined this way. It goes between 0 if the two states are indistinguishable to 1 if the two states are orthogonal. And they define the information flux as the time derivative of the trace distance. And of course, if you have positive information flux, it means that you are gaining some information, you have a backflow of information back to your system. And so non-Markovianity is the integral of the information flux over the time intervals where the flux is positive. And then since you don't want this measure to depend on the initial state of the system, you perform a maximization over all possible initial pairs. And this is the measure of non-Markovianity. Calculate this quantity is very difficult. It's difficult because, yes, it involves an optimization procedure, and you have to optimize over all possible initial pairs. And but for specific case, there is it is known from the literature the analytic, not the solution, but the maximizing pair. For example, in the case of dephasing. And so once you know the maximizing pair, if you want to not to do a quantitative study, but just a qualitative study to say if the dynamics is Markovian or non-Markovian. You can just analyze the behavior of the trace distance. And if the trace distance became monotonically, the information flux is always negative, and so the dynamics is Markovian. But if the trace distance shows as oscillations, so you have intervals of time where the information flux is positive, and so you can classify the dynamics as non-Markovian. So what we did to be able to classify, say something about the dynamics of our system, we consider just one qubit interacting always with a fluctuating field described as a collection of random bistable oscillators. And if you consider a generic initial state, and we can write the dynamics of the two qubit system, and once you have the expression for one qubit, you can calculate this quantity in the case of two. You consider the maximizing pair from the literature, and what you are able then to calculate the optimized trace distance. That is the trace distance calculating for the optimizing pairs. And what you see is that this is the absolute value of the phasing coefficient. Of course, this is a dephasing because the populations are left unchanged, and you have just an extra factor that affects the off-diagonal terms. And again, this lambda is the same as before, actually. It can have monotonic behavior or it can display oscillation depending on the ratio between the switching rate and the coupling constant. And so here I show you some results. In this column, you see the maximized, sorry, the letter is wrong, Studi, is the maximized trace distance in the case of where the environment is described using only one bistable fluctuator. And what you see is that, for example, let's consider alpha equal or greater than 1, but also actually in the case of alpha, which is smaller than 1, you always have oscillations. And the black curve is the 1 over f, alpha equal to 1. And so for a single fluctuator, the dynamics is always non-Markovian.
What means alpha for a single fluctuator? Because alpha was something on the distribution of fluctuators. Alpha was something on the distribution of the frequencies of the...
Yeah, but you can take only one and still obtain the spectrum because the switching rate is random. So what creates this, in the end, the spectrum is because you have this randomness on the value of the switching rate.
This is the average of several experiments with different fluctuators.
With different, yeah, the average
is,
yeah.
This and you will get this.
Yeah, exactly. But if, for example, the switching rate were fixed, because sometimes in the literature you reproduce this kind of noise using a collection of fluctuators, but with fixed switching rates. And in this case, of course, you cannot get 1 over f spectrum using only one, because you will get random telegraphic noise. So yeah. Okay, so the dynamics is, let's say for a single one, is always non-Markovian, and here it's the same graph, 3D graph, where I have the time and the different values of alpha. I put it here because now I want to increase the number of fluctuators. So for example, I consider 50, and what you see is that the behavior this time is different. And for example, 1 over f, alpha equal to 1, you see, okay, maybe it's not so clear, but the trace distance decays monotonically. So the dynamics can be classified as Markovian. While if you have the higher value of alpha, oscillations survive, and so the dynamic is still non-Markovian. And this actually is nice, because if you remember the behavior of the quantum correlations, what you see, okay, let's focus on this graph, is that for alpha equal to 1, if alpha equal to 1, we had a monotonic decay behavior of quantum correlations, and it corresponds to a Markovian dynamics of the system, of the quantum mark. And in the case, for example, alpha different from 1, we had revivals, and it corresponds to oscillations of the trace distance. So what we can say, at the beginning, I said that can non-Markovianity be addressed as a resource from quantum information processing? Our answer for this kind of system, of course, is yes. Because every time you have non-Markovian dynamics, then you have revivals for quantum correlations. So this is something new. And every time you have a non-Markovian dynamics, you have a monotonic decaying correlation. So, okay, and here I showed, I didn't show you before, but it was the case, of course, for one fluctuator, and you see that alpha equal to 1 fluctuators, and you have correlations. So the behavior still match. So well, we can do this one-to-one correspondence between the Markovian or non-Markovianity of the quantum map and the presence of oscillations in revivals in quantum correlation. Okay, now moving. So this was for the non-Markovianity part of the talk. And now I want to move to the last part of the talk, and. So far we have considered a quantum system prepared, for example, in a pure state, and because of the interaction with an external environment, it loses some quantumness feature, it loses some coherence, it loses, for example, quantum correlations decays. And after the because of this interaction, yes, the state, for example, is not pure state anymore, it's described by a density matrix, and it has lost something. So now what we want to do is, since this qubit system, very simple quantum system, are very sensitive to these fluctuations of the environment, the idea is to use them as a quantum probe, for example, to characterize a complex environment, for example, characterize the spectral properties of the environment by performing a measurement after some interaction time. I mean, you prepare a state, an initial state, you let it in quantum state. You let it interact with a complex environment, and then you perform a measurement on the output state, and from this measurement you try to recover, to infer the value of some properties of the environment. For example, the value of alpha. And the idea is to extract the most information possible, and to do that we have to maximize the preparation of the probe. We have to find the optimal interaction time and also to find the optimal measurement. So that allows us to extract the maximum amount of information from the system. And this can be done thanks to the tools of quantum information theory, quantum estimation theory. And the basic idea is that you have a family of quantum states that depends on a parameter, for example, alpha in our case. But the idea, more generally speaking, alpha is an unknown parameter that not only is unknown, but we cannot access it directly. For example, if you want to measure quantum correlation entanglement, you cannot measure entanglement directly. You have to measure something else and then infer the value from this other measurement. So what you do is you collect a series of outcomes, you perform some measurements and collect the outcome, and then you use the outcomes to build an estimator. An estimator is a function of the outcome that allow you to infer the value of the parameter you want to estimate. And how can you say if your estimator is precise, is a good estimator or not? You can say a good estimator has a small variance. But you cannot have a variance as small as you want, because there is a limit to a bound to the variance of every unbiased estimator, which is called the Cramer-Rao bound, and so the variance is bound to the inverse of the Fisher information. This is M is the number of measurements I perform. And so the Fisher information is some classical quantity that I mean, you can also have it classical. And it depends on the conditional probability of finding the outcome X in your experiment when the true value of the parameter is alpha. And what if now you want to do it quantum? If you want, so quantum mechanics give us let's say, the ultimate bound to the precision of any estimator. This is an alpha, sorry. And okay, this is the quantum Kramer-Rao, and what you have to do is substitute the expression of the Fisher information by the quantum Fisher information that I report here in the case of a qubit, otherwise it has a more general form. And if you analyze this expression, you see that the first term, in the case of a qubit, corresponds to the classical Fisher information. You have some self-integral because you only have two levels, and this is done by diagonalizing the density matrix. And then you have a second term, which is quantum, has a quantum nature, and it depends also on the eigenvalues, but also the eigenvectors of the density matrix. And moreover, you say that you have an optimal measurement when the Fisher information associated to that measurement is equal to the quantum Fisher information. So in this case, you say you have your optimal measurement. So now we have all the ingredients we need, and we can consider again a single system, that is a single qubit that is interacting with a complex environment. And a complex environment, I mean, against the stochastic process modeled as a collection of random bistable fluctuators. You consider a generic initial state because we have to do optimize over the state preparation. So we compute the dynamics. Having this density matrix, we compute state m phi, and we find the optimal state preparation. In this case, considering this system described as with this Hamiltonian, which is the state 0. So now we have the dynamics optimized over the state preparation, and what we can do, we can compute the quantum Fisher, which you see depend, of course, on the value of the parameter, depend on the number of fluctuators, and on time. So now we can maximize this quantity on time, of course, and find the optimal interaction time, but we can also find the optimal measurements. And to do that, if you compute the probability of obtaining 0 and the probability of obtaining 1, and you put this expression into the expression of the Fisher information, yes, related to population measurement in the computational basis, you found that this Fisher information is equal to the quantum Fisher information. So the optimal measurement, if you want to perform or simulate an experiment, you have to take population measurement in the computational basis. So we have also found the optimal measurements, and these are our results. Here, okay, I don't show the quantum Fisher, but the quantum signal-to-noise ratio, which is proportional to the Fisher. And this is the case for one fluctuator, and you see that the signal-to-noise ratio has a maximum over alpha equal to 1. So this means that for a single fluctuator, the 1 over f noise is, can be estimated in a very reliable way, in a very precise way. But, for example, if you move to a higher number of fluctuators, not very much, just already 10, what you see is that the peak moves on another value of alpha. And so this doesn't mean that alpha equal to 1 cannot be estimated. But it means that when you build your estimator, its precision will not be very high. So, and then, okay, this is also as a function of time. We optimize this quantity also over time, and displays the behavior of the ratio for different values of the fluctuators. And okay, of course the behavior matches, and for a single fluctuator you can estimate very well alpha equal to 1, or very near values. And if you increase the number, the peaks, you have two local maximum, and these are on different values of alpha. And here in this graph, I also maximize the quantum Fisher for the with respect to, I mean, I found the optimal number of fluctuators you need to obtain them a maximum in the quantum Fisher information. And you see, for example, alpha equal to 1, you obtain, of course, the best value when you just consider one fluctuator. So this is our results for what concerns quantum estimation theory. I'm not giving you a procedure to actually perform an experiment. I'm not giving you the estimator. I'm just showing you the analysis on the quantum Fisher to show you that actually that it is possible. If you find the right estimator, then there are you can, in a more depending on the value of alpha, you can estimate this parameter in a more or less reliable way, of course, depending on the value. And this actually concludes my talk. So, brief conclusion. I told you that there are some cases that are of interest for the quantum information community where the environment needs to be described as classical. You cannot use a quantum description of environment. And I show you the behavior of quantum correlations in this such quantum system interacting with classical environment. And I showed that the recoherence and the oscillations in the quantum correlations is related to the non-Markovianity character of the dynamical map. And then in this last part, I show you that quantum probes can be seen as a resource to characterize classical environment. And the idea is powerful because you measure a very simple system with few degrees of freedom, a simple system which is maybe easily controllable, to characterize a very complex environment. And thank you for your attention.
Thank you. Questions? Any comments?
I did a little bit lost with the construction of the path of the environment.
Yeah.
With this, just to the amount of revival, what happens if you put a purely single fluctuator with an exponential correlation? Yeah, this is why.
This one.
My question, yeah, this one.
Then
my question is because you haven't said. You study 1 over f noise, but you haven't said if 1 over f at short frequencies or at large frequencies. I think this is relevant. This exponential is 1 over f squared at large frequencies.
1 over f squared.
So I don't know which kind of 1 over f noise are you talking about. What happens if you put this exponential?
No, if I put this, only this, with a fixed gamma, I obtain the random telegraph noise.
Yeah, but what happens?
With
I guess you will have revivals.
You have revival? Yeah, it depends because there are two regimes. You can have monotonic decay and you can have revivals. It always depends on the ratio between the decoupling constant and the switching rate. If you put one with random switching rate, okay, the spectrum you build as the expression 1 over f, and the important frequencies. I mean, in 1 over f noise. The important frequencies are always the low frequencies because they are, yes, the spectrum, let's say it's peak, doesn't have a peak, but low frequencies are the more important. Then what is low, okay, depends on the experiments you're performing. But I've read numbers related to, okay, but no, for a single, okay, I can't give you the numbers. I can say it's low, but for a single case.
So I have a question about this information flux.
Yeah, yeah.
So is it manifestly real?
Is it?
I mean, is it real?
A real quantity?
Yes.
Yes, yes. Because it's just the derivative of the first distance.
Okay. And then since this is a flux, does it obey any continuity relation?
They called it flux. They called it information flux. And no, because like it's okay, it doesn't obey like conservation of the energy. Because this is information. So you can lose information, and without if it was energy, yes, you should conserve it. But this is information. So it's not said. It's not. You cannot say. There's not a rule or a constraint that you have to conserve the information. You can lose you can just. I mean, you don't have to think like as if it were energy. Or at least I was taught this way. I was taught this way that you can just consider it lost without saying it goes in like energy. It goes in heat. In here, at least I was told you can. There's no conservation relation that we should.
So it's not information of the, let's say, the whole system?
It's the information of your quantum system that just leaks out of in the environment. It just leaks out.
Yes, I think it's more an analogy. It's not really flux.
Yeah.
Actually, it's just how a distance is changing between states. I also was on the same, no, not the same, but related to what Emilio also was asking. I didn't understand in the noise which was the effect of having more fluctuator than one.
But the effect is that
If you already have that is random, then
I lost it. Okay, the effect that, for example, you can see on correlation is that they die faster.
no, I saw in the correlation, but I didn't understand which was the effect on the noise. What does it change what is changing in the noise when you have more than one fluctuator?
Basically, that you have, let's say, like more decoherence channel. I mean, if you just interact with one fluctuator, it's you have this exchange of, let's say, of information between. You can have this exchange of information between the system and the environment. If you have many, you always lost something, lost some information or some coherence that it's more difficult to recover, like to have a revival.
And then I heard sound in these terms, in this
Yeah.
term. So I didn't see, maybe I missed it.
We consider, okay, the point is, we can reproduce the spectrum using just one random, because there is the randomness on the switching rate, but we consider also a collection, because first of all, you can describe a more realistic scenario, because one fluctuator, it's not said that it corresponds, we started with one fluctuator as a toy model, but then if you read all the literature, they tell you is that it comes from a collection of a bistable fluctuator. So we also wanted to do something in analogy with what is already found in the literature, so we also considered the collections. But the effect is like a multiplicative effect of the single one, because they all are for each of them, their switching rates belong to the statistical ensemble. So it's like when it's like a multiplicative effect. And the effect is that correlations die faster.
Because we get it.
Yeah.
I have one comment regarding these revivals as well.
Okay.
And the transparency now. If I understood from what you said before that you have quite some semi-analytical understanding of the problem, but do you have some more qualitative, more physical understanding of the difference between the alpha equal to 1 to alpha equal to 1/2? I mean, one is you don't have revivals in this independent environment, and the other you have.
Yeah, because
the physical effect.
Okay, this this alpha is larger than this one. It means that if you consider the spectrum 1 over f power of alpha, in this case, lower frequencies are more important. And if you take the okay, so if you consider the expression of the d factor, when you have a very low frequency, the behavior of this factor is that it displays oscillations. And here you have to do the integral is like that you do the summation of many of these terms. And if you are at the very low frequencies, you have like a beat effect when you consider like wave, they sum up. And when the frequency, okay, 1 over f with alpha equals 1 is still low frequency, but not as low as if you consider an higher exponential. And in this case, what we saw, I didn't show here, but what we saw is that the effect of summing these d terms is that they're destructive, like when you have destructive interference of waves. So this is, okay, didn't show it in here, the passages, but what we found was this. That you have like an interference effect and a beat effect. Yeah.
And these results are for the phasing, not this.
Are for the phasing, yes.
But in the probes one, there was sigma x.
But actually, I put the identity on the I cheated, I put the identity, so it's a dephasing in the plus-minus basis.
Yeah. Okay. Any other questions? Okay, let's thank Claudia.